Welcome to this presentation. Today we are going to continue question and answers regarding thermochemistry. Last time we ended on question number 10 and today we are starting question number 11. Question number 11 is saying explain the terms heat capacity, specific heat capacity, molar heat capacity, sensible heat, latent heat of fusion, and latent heat of vaporization. Let's quickly move to the answer. The heat capacity is the amount of heat that is needed to change a substance temperature by 1 degree Celsius or 1 degree Kelvin. So the heat capacity is the amount of heat that you need to change the temperature of a substance by 1 degree Celsius or 1 degree Kelvin. How is it calculated? The heat capacity is calculated by taking the heat dividing with the change in temperature. So from this formula, we can calculate the heat. That means that the heat is equal to heat capacity times the change in temperature. So we are here, the heat is equal to the heat capacity times the change in temperature. When you have the heat capacity, you can calculate the heat, and whenever you have the heat, you can calculate the heat capacity. The next definition that we need to explain is the specific heat capacity. Specific heat capacity is also the heat which is needed to raise the temperature of 1 gram. Here we need to specify the mass. Is the heat which is needed to raise the temperature of 1 gram of substance to 1 degree Celsius or 1 degree Celsius. Here we are referring as the mass. We need to include the mass in the formula. The heat capacity, specific heat capacity, is equal to the Q dividing of the heat or the heat dividing with the mass times the change in temperature. From this definition, then, we can calculate the heat is equal to the mass times the specific heat capacity times the change in temperature. When you have the specific heat capacity, you can calculate the heat capacity as mass times the C, which is specific heat capacity times the change in temperature. The molar heat capacity is the heat needed to raise the temperature of 1 mole. Here is the temperature of 1 mole of substance to 1 degree Celsius or 1 degree Kelvin. For specific heat capacity, it is raising the temperature of 1 gram, and for molar heat capacity, is the heat required to raise the temperature of 1 mole. So then the molar heat capacity is equal to the heat dividing with the number of mole rather than dividing with the mass. For molar heat capacity, we divide with the number of mole times the change in temperature. Molar heat capacity is equal to the heat Q dividing with N, the molar heat capacity times the change in temperature. Then from this formula, we can calculate that the Q, which is the heat, is equal to the number of mole times the molar heat capacity times the change in temperature. So this is different formula that you use whenever you have the heat capacity, a specific heat capacity, and the molar heat capacity. You can be able to calculate the heat. The next, if we have, for example, a substance with high heat capacity, that means that you absorb a lot of energy. When you have the substance with high heat capacity, it will absorb a lot of energy without changing much of its temperature. So that means that, contrary, a substance with very low specific heat capacity will require a small amount of energy to increase the temperature. That's what mean the specific heat capacity or the heat capacity. A substance which has the high heat capacity, that means it is capable of absorbing a high energy, a lot of energy without changing its temperature, while a substance with a very low specific heat capacity or a very low heat capacity will require a small amount of energy just to increase its temperature. Another term is what we call sensible heat. What is a sensible heat? This is the heat exchanged by thermodynamic system in which a change occurs, but that change change only the temperature of the system. It is the heat required to change the temperature of the system without changing the phase. Heat exchanged by a thermodynamic system in which we have the exchange of heat, but this exchange of heat only changes the temperature of the system, but does not change the phase. So this sensible heat only contributes to the increase in the temperature, but no change in the phase. When an object, for example, is heated, there is an increase in the temperature. That's the sensible heat, an increase in temperature without a change in the phase. Similarly, when you remove heat from an object, a temperature decrease, but without decreasing without changing the phase. That's what we are referring as a sensible heat. Sensible heat increase or decrease the temperature, but without changing the phase of the substance. Let's see what is latent heat. Contrary, the latent heat change the phase of the substance. It is the energy absorbed or released from a substance during a phase change. For the latent heat, you should be having the phase change, but for the sensible heat, it's only an increase in temperature without a phase change. We have the latent heat of fusion and the latent heat of vaporization. That means that the latent heat of fusion is the heat provided to a specific quantity of the substance to change its state, but from solid to a liquid. The change is changing from solid to a liquid at constant pressure. That's what you call latent heat of fusion, where is the heat which is required to change the phase from solid to a liquid at constant pressure. So how is it calculated? The latent heat of fusion is F is equal to Q over M. That means the heat dividing with the mass. It is expressed in joule per gram. That means that from this definition, we can calculate the heat by taking the mass times the latent heat of fusion. Q, which is the heat, is equal to the mass times the latent heat of fusion. We have also latent heat of vaporization. That means that is the heat that is required to change the liquid substance from liquid to vapor. So that means that we have a liquid substance and we need to transform or to change that substance to a gas. So that means we are moving from water with water as liquid, and then we need to change the phase. So that means to change the phase of water is to transform it to vapor. So again, that is latent heat of vaporization in joule per gram is equal to the Q, which is the heat expressed in joule dividing with the mass. That means that the Q is equal to the mass times the latent heat of vaporization. So if you check this diagram, we need to have, we start with minus 200. That means that you have ice, and the ice is going to increase its temperature up to 0 degrees Celsius. It is ice with 0. Then it will melt. So that means the temperature required to move from minus 200 to 0 is the sensible heat. Then the ice is going to move from 0 and producing 0 water with 0 degrees Celsius. There is a phase change. Water 0 degrees Celsius to water, the ice with 0 degrees Celsius to giving water with 0 degrees Celsius. Here there is a melting, but also there is a phase change from solid to liquid. And the solid is having 0 degrees Celsius, and water produces also having the 0 degrees Celsius. That means here the heat required to change this phase, that's what you call latent heat of fusion. Then the water with 0 degrees Celsius will increase its temperature by supplying the heat to increase the temperature up to 100 degrees Celsius. Here you will need sensible heat, because sensible heat increases the temperature without changing the phase. Now, this water with 100 degrees Celsius will give the vapor with 100 degrees Celsius. We have the water with 100 degrees Celsius will give vapor at 100 degrees Celsius. So we are changing the phase, water to vapor. Here we need what we call latent heat of vaporization. Then after here, then we will have vapor at 100 degrees Celsius, which will increase temperature to vapor at 300 degrees Celsius. This means that here, the last stage, we need also the sensible heat. So then, from melting, when you melt, you are changing the phase, you have the latent heat. Again, when you have, for example, you have evaporation, you are changing from a liquid to gas. In that case, you are having also the latent heat. The sensible heat is the place where you increase the temperature without changing the phase, increase the temperature without changing the phase, and here also there is increase of temperature without changing the phase. Let's go to question 12. Question 12, what is this saying? Question 12 is saying we have 50 grams of water was heated from 20 degrees Celsius to 80 degrees Celsius. The specific heat capacity of water is given as 4.184 joule per gram degree Celsius. How much energy is required to heat these 50 grams of water from 20 degrees Celsius to 80 degrees Celsius? Let's move to the answer. We have the formula where the Q, which is heat, is equal to the mass times the specific heat capacity times the change in temperature. Now they are asking the heat, how much heat. We need then to replace the values. The mass, we have it as 50 gram. We have the specific heat capacity of water, which is 4.184 joule per gram degree Celsius, and you have the change in temperature from 80 degrees Celsius minus 20 degrees Celsius. Then, if we are calculating, we immediately get 12.552 kilojoule. You are converting joule to kilojoule by dividing by 1,000. So, the formula of calculating the heat. So, let's go to another question, which is number 13. Number 13 is saying 3 kg of ice at 0 degrees Celsius was converted to water at 30 degrees Celsius. Half kilogram ice at 0 degrees Celsius convert to water at 30 degrees Celsius. But 3 kg of ice at 0 degrees Celsius has to pass through to melt and producing water with 0 degrees Celsius before increase the temperature to 30 degrees Celsius. The latent heat of fusion of water was given at 334 joule per gram, and the specific heat capacity of water was given at 4.184 joule per gram degree Celsius. Now the question is asking how much energy is required to convert ice to water at 30 degrees Celsius. Here we have a two phase. Let's go to the answer. Here we have the heat is required to convert ice at 0 degrees Celsius to water with 0 degrees Celsius. So we have 3 kg of ice at 0 degrees Celsius, and it will melt to produce water with 0 degrees Celsius. You have ice with 0 degrees Celsius to produce water with 0 degrees Celsius. That is the phase change. In that case, we are going to use the latent heat of fusion. So in that case, the Q which is required to melt the ice to compute the phase change will be equal to the mass times the latent heat of fusion. So we need to change the mass into gram. 3 kilogram, it is equal to 3,000 gram. Then times the latent heat of fusion. Then you get 1 times 10 power 6 joule as the heat which is required to change the phase to melt the ice. Then after melting the ice, we have water with 0 degrees Celsius. Then the heat is also required to increase the temperature from 0 to 30 degrees Celsius. That means that for the first stage, this is the heat required to phase the change. This is the latent heat of fusion. This is the heat required to phase to change the phase. So in that case, we will use the latent heat of fusion. So then the heat is equal to the mass times latent heat of fusion. So the latent heat of fusion was given. From this value, then you can determine the latent heat of fusion, although here it was given, but if it was not given and you have the Q, then you can calculate also the latent heat of fusion if you have the mass. Now, the heat is also required to change the water from 0 to 30 degrees Celsius. In that case, we have the Q, which is equal to the mass times C times density. So that means that we need to have the mass in gram times here the specific heat capacity of water times the change in temperature. Here the change in temperature is 30 minus 0, so we have 30 degrees Celsius, and we get 3.77 times 10 power 5 joule. Then the total heat, then we add the heat required, the heat from latent heat of fusion, the heat required to change the phase, plus the heat required to increase the temperature. Then we have 1.38 times 10 power 6 joule as the total heat which is required to change 3 kg of ice at 0 degrees Celsius to 30 kg to 30 degrees Celsius water. Let's go to question number 14. Question number 14 is saying 4,000 joule of energy is applied to 70 gram of sample of water, which was initially at 35 degrees Celsius. We have initial temperature was 35 degrees Celsius. What is the final temperature of the sample? The specific heat capacity of water is 4.184 joule per gram degree Celsius. Here we have the heat. So if you have the heat, then we need to calculate the final temperature of the sample. So the heat is equal to mass times the specific heat capacity times the change in temperature. Then here the change in temperature, we need to calculate the TF minus the T initial, and T initial we have, mass also we have, and the C also we have. So here we put the joule, which is the Q, it was given as 4,000. We have the mass, which is 70 gram. We have the specific heat capacity, which is equal to 4.184. We have also the TF minus T initial, temperature initial was given as 35. Then we need to rearrange the terms and find TF. If we do the calculation, we will see that the TF or final temperature will be equal to 48.66 degrees Celsius. Let's end to question number 15. Question number 15 is saying it takes 30 calories of energy to heat a 13.2 gram of sample of unknown metal from 18 degree Celsius to 49 degrees Celsius. You have an increase in temperature, and you are having the mass of the unknown metal, which is 13.2 gram. And we have also the energy, which is the heat. What is the specific heat capacity of unknown metal? So we need to calculate the C. Here we also use the formula, but the heat is 30 calories. We need to convert to kilojoule. So we know Q is equal to MC dt. That means that the C, which is the heat capacity, is equal to Q dividing with M, which is the mass times the delta T. Or here all the information is there we have, but we need to convert the calorie to joule. In that case, 1 calorie is equal to 4.184 joule. So 30 calorie is equal to 30 calorie times 4.184 joule per calorie. In that case, we get the heat equal to 125.52 joule. Then we replace C will be equal to Q dividing with the mass times the change in temperature. The Q, the heat, was calculated as 125.2 joule. This is 30 calories that we have converted to joule. Dividing with the mass was given as 13.2 gram times the change in temperature is 49 minus 18 degrees Celsius. Then you will get the heat, the specific heat capacity, which is equal to 0.3067 joule per gram degrees Celsius.